into the wild world. That's the study of trees. Why don't you jot that down for your SATs?
Section B, Tree Diagrams and Prime Factorization.
We're about to use tree diagrams to get smart about prime numbers. Tree diagrams help us break big composite numbers down into the product of smaller prime numbers with exponents.
We call them tree diagrams because they sort of look like little trees with branches, except they have numbers on them. We start at the top of the tree with a big composite number and work our way down the branches, getting smaller and smaller until we have merely twigs with prime numbers. Check it out.
Say we've got the composite number 72, and we factor it down to 12 and 6. We can't go home yet because these numbers are also composite, and we gotta factor until we've got all prime numbers. So, 12 will factor into 4 times 3, and 6 factors into 2 times 3. Then our 4 factors down even further into 2 times 2. So now we've got 2 times 2 times 3 times 2 times 3. Notice we're now at the point where we have all prime numbers. The next step is to express those numbers exponentially. In other words, to write them as base numbers with exponents. Since we have 3 2's, that gives us 2 to the third power, or 2 cubed. And we have 2 3's, so we have 3 squared. That means the prime factorization of 72 equals 2 cubed times 3 squared.
Now, how do we know to start with 12 and 6 in that last example? Well, we could have started with 8 and 9, which are also 2 factors of 72, and gotten the same answer. It's not important which 2 factors of 72 we start with, only that we get started. Once we complete the factor tree, if we did it right, we'll get the same prime factorization either way.
So our goal is to get big composite numbers factored down into a product of prime numbers with exponents. Let's give it another go. Check out the tree diagram for the number 81.
If we factor 81 using the tree diagram, we start with the factors 9 times 9. Notice these aren't prime numbers, so we've got to keep going. Since 9 can be factored into 3 times 3, we get 3 times 3 times 3 times 3, or 3 to the 4th power. If we multiply it out, we see that 3 to the 4th power equals 81, which means we factored correctly, because 81 is our original number.
Now let's try a big scary number like 336. With a big scary number like this, if it's an even number, the easiest thing to do is just keep dividing by 2 until we can't anymore.
Dividing by 2, we see that 2 goes into 336 168 times. So, our first 2 branches are 2 and 168. Now, we can break 168 into 2 times 84. 2 goes into 84 42 times, so these are on our next branches. 42 can be broken into 2 times 21. Now, notice that 2 doesn't divide into 21 evenly, but we can still break 21 down into smaller numbers. We know that 7 times 3 equals 21, so we factor it by breaking it down to 7 times 3. Neither 7 nor 3 can be broken down any further because they're both prime numbers. That's good. It's what we want. But we're not done just yet. You see all those 2's? We can't forget about them. They're still part of our prime factorization, so we gotta include all 4 of them in our answer. When we do, the ultimate prime factorization of 336 is 2 to the 4th power times 3 times 7. If we want to check our work, we can multiply this out to get 2 times 2 times 2 times 2 times 3 times 7 equals 336. Since our numbers equal 336, we know we did it correctly. Now, our big scary 336 isn't really that big or that scary.
With the prime factorization of a composite number, you've got to get all the way down to the nitty-gritty of it. You're only finished once you've got all prime numbers and you've given them the right exponents.
Okay, now that we know how to find all the factors of a composite number and how to find prime numbers, let's step it up a notch.
Section C, the greatest common factor.
The best way to introduce the greatest common factor is to pick a couple numbers and factor them like we've been doing. The greatest common factor is going to be the factor with the highest value, or largest quantity, that appears in both lists of factors. Let's try this with the numbers 15 and 20.
Our first step is to factor both our numbers. We're going to do the listing method this time, so let's list the factors of 15 and 20. The factors of 15 are 1, 3, 5, and 15. And the factors of 20 are 1, 2, 4, 5, 10, and 20. The next step in finding the greatest common factor is to figure out all the factors that these two numbers have in common. In this case, we notice that 1 and 5 are in both lists, so they're called common factors. Now remember, the greatest common factor is the one out of these two that has the highest value. In this case, the greatest common factor is 5 because it's a common factor of 15 and 20, and it's greater than the other common factor, 1.
Another thing to know about the GCF is that it's possible the GCF of two numbers will equal 1.
For example, with the numbers 7 and 15, 1 is the greatest common factor because after we factor them out, we see that 7 and 15 have no other factors in common. So, 1 is both their only common factor and their greatest common factor.
Since we found the GCF in our previous examples by listing factors, now we're going to try another way. Remember way back about 3 minutes ago? We used the tree diagrams to do prime factorization. Well, we're going to use that same prime factorization stuff to help us find the GCF another way. Let's take a look.
Say we're searching for the GCF of 12, 28, and 48. First, we're going to factor them down to prime numbers using the tree diagram, and then put them into numbers with exponents. So, starting with 12, 12 breaks down to 6 times 2, which further breaks into 3 times 2 times 2, or 3 times 2 squared. 28 equals 14 times 2, which breaks into 7 times 2 times 2, or 7 times 2 squared. And 48 equals 12 times 4, which breaks into 4 times 3 times 2 times 2, which equals 2 times 2 times 3 times 2 times 2, or 2 to the 4th power times 3. Now let's figure out the GCF.
After we get the prime factorization, we've got to look at the numbers and their exponents and figure out which will be a part of the GCF. Any prime factor we choose for our GCF must be a factor of all three of the original numbers because that's what makes it a common factor. So, when we look at the prime factors, we see that 2 is the only one that's a factor of all three numbers. So it's going to be the lone base number in our answer. The only thing left is to figure out what exponent 2 will have.
When deciding on the exponent, we look at the exponents for each of the 2's. We've got 2, 2, and 4. To get the GCF, we just take the smallest exponent. So in this case, we would use 2 as our exponent. That means our GCF is 2 squared.
So, our GCF, 2 squared, equals 4 when we multiply it out. 4 is the greatest common factor of 12, 28, and 48 when we express the GCF in whole numbers.
A great way to check our work is to list the factors like we did in the first method and see if we got the same answer. See how when we list out the factors in whole numbers, 4 is the GCF. That means we did our factoring correctly.
So, when we're looking for the GCF, first we want to get the prime factorization of our numbers. Then figure out which prime numbers are factors of all our original numbers and how many times each of those prime numbers is represented. Then, we take the smallest exponent and we've got our GCF. Now we're going to take a look at something that's kind of like the cousin of the GCF, but with its own identity.
Section D, the least common multiple.
Before we get into the least common multiple, or LCM, let's take a minute and talk about what a plain old multiple is. A plain old multiple is what you get when you multiply one number by another number.
All right, let's take the number 3. What are its multiples? Well, 1 times 3 equals 3. 2 times 3 equals 6. 3 times 3 equals 9. 4 times 3 equals 12. 5 times 3 equals 15. 6 times 3 equals 18. 7 times 3 equals 21. And 8 times 3 equals 24. So the first 8 multiples of 3 are 3, 6, 9, 12, 15, 18, 21, and 24.
And now, it's the artist formerly known as the least common multiple. Give it up for the LCM. To find him, just look in a few lists of multiples. He's the number with the smallest numerical value that appears in all your lists. Take a look.
These are some multiples of the numbers 6, 10, and 15. What we want to do is figure out the least common multiple of all three. So, the LCM is the multiple that 6, 10, and 15 all have in common and has the smallest numerical value. You might notice that 60 is a multiple in all three lists, but so is 30. Because we're smart, we know that 30 is smaller than 60. And 30 is the smallest multiple they all have in common, which means 30 is the LCM of 6, 10, and 15.
When you're listing multiples, the fastest way to find the least common multiple is to look at the multiples of the largest of the numbers. So, for our previous example, to find the LCM of 6, 10, and 15, 15 is the largest number, so you would look to the multiples of 15. First, try 1 times 15, or 15. 15 is not a multiple of 6 and 10, so next try 2 times 15, or 30. 30 is a multiple of both 6 and 10, as well as 15, so our number is 30.
Listing multiples, like we just did, is one way of finding the least common multiple, but there is another way to do it. Any guesses?
Look in the back of the book.
Nice, but no. We're going to use the prime factorization method. Let's use the same numbers, 6, 10, and 15. Now remember way back about 2 minutes ago when we found the GCF? Well, our first step here is the same. We're going to factor with tree diagrams and then give our prime numbers exponents.
So, if we take 6, we get the prime factors 2 times 3. 10 breaks down to 5 times 2, and 15 gets mapped out so that its prime factorization is 5 times 3.
Now we've got all our prime factors and we need to express them with exponents. This part is a little different from the greatest common factor. To represent the LCM with prime numbers exponents, we need to take every prime number that appears as a prime factor and write it once with the biggest exponent that appears. Take a look.
Since the prime numbers we see are 2, 3, and 5, we're going to use each of these one time and give them an exponent. For the LCM, we use the biggest exponent for each prime number that is represented. This is different from the GCF, where we use the smallest. Notice in this example, the most each prime number appears in a single factorization is 1 time. So the biggest exponent we can use for each is 1. That means the LCM of 6, 10, and 15 is 2 to the first power times 3 to the first power times 5 to the first power, or 2 times 3 times 5. See how when we multiply 2 times 3 times 5, it equals 30, which is what we got before when we compared multiples with whole numbers.
Excuse me.
Dude, get the mustard, dude!
When you multiply your prime numbers with exponents, they equal my whole number. I checked it out.
What now, dude?
There's nothing left now but math. Hey, let's get the LCM of 10 and 25.
Doing the prime factorization of 10 and 25, 10 breaks down to 2 times 5, and 25 breaks down into 5 times 5, or 5 squared. At this point, we're already down to our prime numbers, so we want to represent all the prime numbers that appear. In this case, we've got 2 and 5. So what is the most number of times 2 appears in a single factoring? Well, it's just 1 time. That means our exponent for 2 is 1. What about 5? The most 5 appears in a single factoring is 2 times, so 2 is our exponent for 5. That means the LCM of 10 and 25 is 2 times 5 squared. If we multiply the LCM out, we get 2 times 5 times 5, which equals 50. And remember, we can check the LCM by listing the multiples out this way. And here we see that 50 checks out as the LCM.
Ta-da! So that's how we find the LCM. We do the prime factorization of our numbers, then represent all prime numbers with their highest exponents. Now fancy this. It's already time for a review of this. So sit back and absorb.